right, today we're going to cover the paper 4. This is the extended theory paper for IGCSE Chemistry. This is the Cambridge International Examinations, and this is for May-June 28, and the code is 0620/41. All right, let's begin. Question 1. Substances can be classified as elements, compounds, or mixtures. A. What is meant by the term compound? Okay, a compound is a substance that's made from 2 or more elements. So it's a substance made from 2 or more elements. And the key word there is elements, not atoms, because O2 is not a compound. It is a molecule, but it's not a compound. CO2 is a compound, okay, because it has a carbon and an oxygen. Those are 2 different elements. All right. B. Mixtures can be separated by physical processes. A sequence of physical processes can be used to separate common salt, sodium chloride, from a mixture containing sand and common salt only. Give the order and the correct scientific term for the physical processes used to separate the common salt from a mixture. So physical processes means there's no reaction happening. So if you have a beaker, and in it you have some salt and you have some sand, you can't exactly pick the 2 out. But the one thing you know is sand does not dissolve in water and salt does. So the first thing you want to do is dissolve the salt. So the process you're looking for is called dissolving. Okay. The second thing you'd want to do then is you have salty water and sand. So you'd want to filter out the sand. Okay. So that's filtration. And third thing, if you want to get pure salt and pure sand, well, you have the sand and the salt. You can remove the water by evaporating or crystallizing the salt. Evaporating the water or crystallizing the salt. Either one would work. They're the same thing, really. So evaporation of the water, or you can say crystallization. All right, either works. Good. So the boiling points of 4 different alcohols, A, B, C, and D, are shown. So we have alcohol A, B, C, and D, and they boil somewhere between 56 degrees Celsius and 160 degrees Celsius. So C, a student suggests that the apparatus shown could be used to separate the mixture of alcohols. All right, so we have our water bath with our heater, and we have the alcohols all mixed together down here, and they evaporate because it gets warmer, and they'll evaporate at different temperatures. This is our fractionating column, which slows down the evaporation, and it makes it so that the water can condense, the alcohol can condense into this little tube here, and then drip down into being collected into the flask. Okay? All right. CI. Apparatus X needs to have cold water flowing through it. Draw an arrow on the diagram to show where the cold water enters apparatus X. All right, and the next thing it's going to look for is the name of apparatus X. Apparatus X is called the condenser because it condenses the alcohols into a liquid form. It's cooler, so the alcohols are no longer gas, they turn to a liquid. So looking at apparatus X, where does the water enter? Where does the cold water enter? So we have 2 options for where we can have the cold water enter. It can either go at the top or at the bottom. Now, which one should it be? If it enters at the top, then it starts off cold and slowly gets warmer as it goes down. If it goes in at the bottom, it's really cold at the very bottom. It might get slightly warmer as it goes up. But just when the alcohol is about to leave through the end, it's going to be at its coldest. So we want the water to enter, the cold water to enter through this bottom hole, this bottom section. Okay, and the water is there, and it comes up here, it goes around, doesn't mix with the alcohol, but it goes around the alcohol and comes out here. Okay, so what they want is they want this arrow here. They don't want an arrow up here. All right. Okay, so we've drawn where the cold water enters. We've named apparatus X. So part 2, part of the fractionating column is missing. This means that the experiment will not work. Draw on the diagram the part of the fractionating column which is missing, and then explain why the experiment will not work with this part of the fractionating column missing. Okay. Okay, so it says part of the fractionating column here is missing. What is missing? So what's going to happen is the alcohol is going to evaporate, and it's going to evaporate, and it's going to evaporate, and it's going to evaporate, and you're going to lose it all. And that's not what you want to do. You want it to evaporate and then condense and then drip down through this little tube. Okay, so what you need is a stopper, a rubber stopper, or cork stopper, it doesn't really matter, just a stopper. All right, that's what you need. And so the next step is explaining the purpose of this stopper. So the purpose of the stopper is because the gases and the vapors from the evaporating alcohols will escape if you don't have it in. So it won't pass to the condenser. Okay, so the gases and vapors will escape, so it won't pass to the condenser. Okay, part 3, suggest why a Bunsen burner is not used to heat the flask. So normally in a chemistry lab, you'll see a little flame under here, and that's from a Bunsen burner. But instead of that, they have an electric heater. Why is that? Well, that is because alcohol, which you're heating here, is very, very flammable. And it can be very, very dangerous if those alcohol vapors catch on fire. So an electric heater just heats them up, changes the temperature. It saves a lot of safety concerns there. So the mixture of alcohols is flammable, so that's why they don't use a Bunsen burner. And as an interesting side note, if you'd written inflammable, that would also be correct, because flammable and inflammable mean exactly the same thing in the English language. But this is science, this is not an English lesson, so it doesn't matter why. If you want to say inflammable, that would also work. All right, continuing on. Part 4, a hot water bath cannot be used to separate alcohols C and D, and explain why. Okay, let's look at alcohol C and D. So alcohol A evaporates at 56 degrees, B at 78 degrees Celsius, C at 122 degrees Celsius, and D at 160 degrees Celsius. But a water bath, really the maximum temperature they generally go to is 100 degrees Celsius, because that's when the water boils. All right, so 122 and 160 degrees, that's not going to work with a water bath. So a water bath does not go above 100 degrees Celsius, which is boiling. And if you notice, this is a 2-mark question. So if you'd just written the first bit in there, that would really only be 1 mark. I can't see how they'd give you 2. So it says explain why. You need to give an example. So C separates at 122 degrees Celsius and D separates at 160 degrees Celsius. That will give you 2 marks. It explains why 100 degrees Celsius is not good enough. All right. Question 2. Flerovium, Fl, atomic number 114, was first made in research laboratories in 1998. Part A, flerovium was made by bombarding atoms of plutonium, Pu, atomic number 94, with atoms of element Z. So what did they do? They took atoms of plutonium, Pu 94, and they bombarded those with atoms of element Z, which is unknown, a mysterious element Z, and they got flerovium, Fl 114. Okay. The nucleus of 1 atom of plutonium combined with the nucleus of 1 atom of element Z, okay? That's what we have up here. This formed the nucleus of 1 atom of flerovium. That's what we have here. So suggest the identity of element Z. Okay, as you should know, the atomic number and the mass number, they're always conserved in reactions. Okay, so we have 94 plus something equals 114. So something equals 114 minus 94, which equals 20. So Z, element Z, is element 20. Now we have to look at the periodic table to figure out which one this is. Okay, so element 20, we're looking at the atomic number or proton number. That is right here. So element 20 is calcium. All right. So the answer they're looking for is calcium. Okay, good. B, in which period of the periodic table is flerovium? Okay, periodic table again. Okay, so I'm using this periodic table. It's prettier, and the one on the exam is on its side, which makes it much more complicated. So, but if you might notice, flerovium is not on this periodic table. Doesn't mean it doesn't exist, but it is there. It's right under lead. But if in the exam, this is on the periodic table, so it's okay. So Fl 114. Oh, all right. So flerovium 114 is right here. What that means is that we need to figure out which period that's in. Okay, so we have the groups at the top, but these are groups. And going down the side, these are periods. So we have period 1, period 2, 3, 4, 5, 6, 7. Okay, so flerovium is in period 7. It's in period 7. All right, good. Next is predict the number of outer shell electrons in an atom of flerovium. And again, that's a periodic table. Okay, so when you want to look at the outer shell electrons, you need to look at the group. So this is group 1, 2, 3, 4. So flerovium is in group 4, which means it has 4 outer shell electrons, just like carbon and silicon and germanium and tin and lead. All right, fantastic. Okay, so there are 4 outer shell electrons because it's in group 4. Good. D. 2 isotopes of flerovium are flerovium-286 and flerovium-289. The nuclei of both of these isotopes are unstable and emit energy when they split up. State the term used to describe isotopes with unstable nuclei. Okay, when you're talking about unstable nuclei that emit energy when they split up, you're talking about radioactivity. And these are isotopes, so we are talking about radioisotopes. One word, radioisotopes. All right. So to complete the table to show the number of protons, neutrons, and electrons in the atoms of the isotopes shown. Okay, so flerovium-286, they already told us up above that the atomic number or the proton number is 114. So if the proton number or the atomic number changed, it would be a different atom. So that's not going to change regardless of what the isotope is. Okay, so as it's the proton number, the number of protons is 114 in both of those. As it's an atom, not an ion, number of electrons is also 114. And this is the only number that changes, the number of neutrons. Okay, so we have the mass number equals the number of protons plus the number of neutrons. We're looking for the number of neutrons, so neutrons equals the mass number minus the proton number, minus the number of protons. Okay, so for flerovium-286, that is 286 minus 114, and that equals 172. And for flerovium-289, that's 289 minus 114, and that equals 175. Okay, so we have 172 and 175, and that's it. Good. E. Only a relatively small number of atoms of flerovium have been made in the laboratory, and the properties of flerovium have not yet been investigated. It has been suggested that flerovium is a typical metal. E1. Suggest 2 physical properties of flerovium. So suggest 2 physical properties of a typical metal. Yes, there are exceptions, but we're talking typical metals. Okay, so I'm going to say typical metals conduct electricity. Okay, and typical metals are also ductile. They can be pulled into wires, basically, into long, thin wires. Okay, other things you could put, there's so many things that are typical metallic properties, physical properties. You could say they have a high melting or boiling point. You could say they're hard. You could say they're dense. You could say they conduct heat or thermal energy, that they're malleable, so you can bash them into different shapes. They're sonorous, they can make sounds when you bang them. They're lustrous or they're shiny. So any of those would work, but you only want 2 because the question only asks for 2. Okay, and then it says suggest one chemical property of fluorovium oxide. So fluorovium oxide is a metal oxide, and metal oxides are basic. So it's a basic oxide. And what that means is if you take the metal oxide and you dissolve it in water, you will get an alkaline solution. And that's all that means. And that's just a typical property of metals. All right, good. Let's move on to question 3. Question 3. This question is about iron. So A, 3 of the raw materials added to a blast furnace used to extract iron from hematite are coke, hematite, and limestone. Okay, so coke is basically just carbon. Hematite, the formula for that is Fe2O3, and that's where you're getting the iron from. And limestone, which is calcium carbonate. Okay, name one other raw material added to the blast furnace. Now, the other material they're talking about here is hot air. Doesn't really sound like a material, but it's absolutely essential. So it is a material. Okay, without the hot air, you wouldn't get the reactions you need. And it's not just heating, you need the air, the oxygen. Okay, good. B, a series of reactions occurs in a blast furnace during the extraction of iron from hematite. Describe these reactions and include one chemical equation for the reduction of hematite and one chemical equation for the formation of slag. So the first thing that happens is coke is burned to form carbon dioxide. So that is carbon plus the oxygen, because when you burn something, it's reacting with oxygen, produces CO2. Okay? The second thing that happens is carbon dioxide is reduced by adding more coke to form carbon monoxide. Okay, so that is, you have the coke, the carbon, plus the CO2, and that ends up producing carbon monoxide. So the next thing that happens is that hematite is reduced by carbon monoxide to form iron and CO2. Okay, so this is the first chemical equation that they want to see. So what's the chemical equation for this? It is Fe2O3 plus 3 carbon monoxide produces 2 Fe plus 3 CO2. And if you're unsure, just double check a few things. There's 3 carbons on this side, 3 carbons on this side, 2 irons over here, 2 irons over here. We have 3 plus 3 oxygens, so that's 6 oxygens. And we have 3 times 2, that's 6 oxygens. Okay, good. So that is the reduction that they want to see of hematite. And so that's the iron they're looking for. But then there's some other reactions that happen as well. It doesn't end there. So limestone, which is one of the other raw materials added, decomposes to form lime and carbon dioxide. So that's CaCO3, that's limestone, decomposes, just breaks down because of the heat to form CaO plus CO2. Okay, and CaO, that's the lime. All right, and then slag is formed when the calcium oxide reacts with silicon dioxide, and that's just a normal impurity that's often found in a lot of these raw materials. So slag is formed when lime reacts with silicon dioxide. Okay, and this is the other reaction they want to see, so you have to know that reaction. Okay, so that's CaO, which is lime, plus silicon dioxide, SiO2, produces CaSiO3. Okay, and that's known as part of slag. All right, good. C, the iron extracted C. The iron extracted from hematite using a blast furnace is impure. Identify the main impurity in this iron and explain how it is removed in the steel-making process. So the main impurity is carbon. Okay, how is it removed? Well, what they do is they pass oxygen through the molten iron, and so the oxygen will react with the carbon to form carbon dioxide. And as we all know, carbon dioxide is a gas, so it escapes. That's it. So you pass oxygen through molten iron to form carbon dioxide, and carbon dioxide is a gas, so it escapes. And you don't have the carbon impurity anymore, and you just have the nice, pure iron that you wanted in the first place. Okay, good. Let's move on to question 4. Question 4. This question is about masses, volumes, and moles. Okay, so which term is defined by the following statement? The average mass of naturally occurring atoms of an element on a scale where carbon-12 atom has a mass of exactly 12 units. Okay, what it's looking for there is the relative atomic mass. Okay, it's looking for the relative atomic mass, not formula mass, molecular mass, because it's talking about one atom of carbon. Okay. B. Butane, C4H10, has a relative molecular mass of 58. Potassium fluoride, KF, has a relative formula mass of 58. Explain why the term relative molecular mass can be used for butane but cannot be used for potassium fluoride. Okay, quite often we say relative molecular mass just as a short form, but it's wrong if it's the wrong type. Okay, so the reason why is because C4H10 is a covalent molecule. Okay, C4H10 is a covalent molecule, which means it has a fixed size. Okay, but KF is ionic. What that means is KF forms large crystals. And so it's hard to say exactly how much KF is in one molecule, I guess you could maybe say, but it's not a molecule, it's a crystal of KF. Okay? So that's why you can't use the term molecular mass for KF, but you can use it for C4H10, for butane. Okay? Good. C. A 0.095 gram sample of gaseous element Y occupies 60.0 centimeters cubed at room temperature and pressure. Determine the number of moles of element Y in 60.0 centimeters cubed. Okay, so for this, you need to remember how you calculate moles for a gas. And so we have moles equals the volume over the molar gas volume. Okay, now if you look at this, the volume they give you is 60.0 centimeters cubed. But when you're talking about molar gas volumes, you want it in decimeters cubed. So 60.0 centimeters cubed equals 0.060 decimeters cubed. Okay? All right. So we can put that into our formula. So 0.060 decimeters cubed divided by the molar gas volume. And the molar gas volume at room temperature and pressure is 24 decimeters cubed per mole. All right. And if you look at that, the decimeters cubed cancelled out, the mole goes to the top, so the answer will be in moles. And so that number equals 0.0025 moles. Okay, so the answer here, you can either leave it at 0.0025, or you can say 2.5 times 10 to the minus 3 moles. Either is okay. All right. So the next part of this is to calculate the relative molecular mass of element Y, and hence suggest the identity of element Y. Okay, so how do you find the relative molecular mass? Okay, so MR equals mass over the number of moles. So you're told in the question that the mass is a 0.095 gram sample. Okay, and you've just calculated that you have 0.0025 moles. That will give you an answer of 38 grams per mole. Okay, now the relative molecular mass here, 38 grams per mole. Don't forget the units. So if that's the relative molecular mass, we need to find the identity of element Y. Okay, that is, again, looking at the periodic table. Okay, so if we look at this, there is no element with a mass number of 38. We have 35.5 at chlorine, 40 at argon, 39 at potassium, and 40 at calcium, but none with 38. And they want a mass number of 38. They don't want you just to guess one that's close. Okay, so let's try a different method. Let's say the molecule is actually made up of two atoms put together of the same element. Okay, so let's try 38 divided by 2. 38 divided by 2 is 19. We have fluorine right here. And fluorine, if we have F2, that gives you a relative molecular mass of 38. Check. We also know that it's a gaseous element, and we know that fluorine is a gas at room temperature, so that's also check. So fluorine is the answer they're looking for. So the identity of element Y is fluorine. Good. All right, fantastic. D, a 1.68 gram sample of phosphorus was burned and formed 3.87 grams of an oxide of phosphorus. Calculate the empirical formula of this oxide of phosphorus. Okay, so we know we have phosphorus plus oxygen, because that's what it means when it says burned, produces PXOY. We need to figure out what X and Y are. Okay, so first of all, we can write a little table. I always find it easier to do this by creating a little table. Okay, doesn't have to be super neat, but it just helps keep things organized. So you know that you have 1.68 grams of phosphorus. You know that at the end you have 3.87 grams of the phosphorus oxide. And as mass is not created or destroyed, it has to react with the same mass of oxygen. So that oxygen is 3.87 minus 1.68, which equals 2.19 grams of oxygen. Okay, so that's the first bit. So now that we know how the mass, let's use that to figure out the number of moles of each. Okay, so remember, moles equals mass over the molecular mass, or the atomic mass, MR or AR. Okay? All right, so we have 1.68 grams over 31 grams per mole, and that's just from the periodic table. So phosphorus here, 31 grams per mole. Okay, right up here, mass number. Oxygen, mass number of 16 grams per mole. Okay, so that equals 0.054 moles. Okay, now the number of moles of oxygen, we have 2.119 grams divided by 16 grams per mole, because we're not looking at the oxygen molecule here, we're actually looking at the oxygen atom, because over here we want to figure out how many oxygen atoms there are. Okay, so that's why we have it as 16. Okay, we want to know how many oxygen atoms there are in relation, not molecules. Okay, so the answer is, for that, 0.136875 moles. And that's a silly number. That's a ridiculous number. So here, with 2 significant figures there, or 3 significant figures there, sorry, we have 0.137 moles is a much better number. All right, so now that we have that, what we can do is we figure out the ratio. That's our third column in this table. Not perfect, I know, but this is just to keep things organized. Okay, so the ratio of P to O. So when we look at the ratio, we look at the number of moles of both of these. So we have 0.054 moles, and we have 0.137 moles. Okay, we want to divide those by the smallest number of moles. So this is 0.054. If we divided it by the larger one, we would get a number less than 1. So it has to be the smaller one. So that equals 1, 2, and if you, so 0.137 divided by 0.054 equals 2.5. Now, the empirical formula includes whole numbers, not fractions, so that if we multiply them both by 2, that equals 2 to 5. So the empirical formula of the phosphorus oxide is P2O5. All right. Good. E, another oxide of phosphorus, has the empirical formula P2O3. One molecule of this oxide of phosphorus contains 4 atoms of phosphorus. Calculate the mass of 1 mole of this oxide of phosphorus. Okay, so we have P2O3. It has, with 4 P atoms, that equals P4O6. Because we need 4 phosphorus atoms. We've had to multiply the number of atoms in the empirical formula by 2, so we have to do the same with the oxygen. Okay, so now we just find the relative molecular mass of this molecule. So the relative molecular mass equals 4 times the mass of phosphorus plus 6 times the mass of oxygen. Okay, so that's 4 times 31 plus 6 times 16, which equals 220 grams. Okay, so the mass is 220, and grams is already given to you. All right, good. So 5a, the table gives some chemical properties of transition elements and their compounds, and of group 1 elements and their compounds. So what is meant by the term catalyst? Because some of these act as catalysts and some of these don't. So a catalyst is a substance that speeds up a reaction without being used up. All right, a substance that speeds up a reaction without being used up. Good. And give one other chemical property shown by transition elements which are not shown by group 1 elements. Okay, transition elements, as I've already said, they can be catalysts, they can act as colored compounds. The other chemical property they can have is they can have variable oxidation states. And this is why they can act as catalysts and exist as colored compounds. Okay, good. Okay, B, give 2 physical properties shown by transition elements which are not shown by group 1 elements. Okay, so transition elements are very hard and they're very dense. Group 1 elements are very soft and they're not very dense. You can also say that they're stronger or that they have a higher melting or boiling point. All right. And C, the energy level diagram shows the energy profile for the reaction between zinc and dilute sulfuric acid. Part 1, complete the diagram by adding the formula of the products and include state symbols. Okay, so we have zinc plus sulfuric acid. Well, that will produce hydrogen gas plus zinc sulfate, which is the sulfuric acid was aqueous, so this is also aqueous. All right. 2, draw an arrow on the diagram to represent the activation energy. Okay, the activation energy is the energy required to start the reaction. So this arrow is what they're looking for, an arrow from the line of the reactant's energy to the top of the hump here. Once it gets that energy, the reaction will continue. Okay, so is this reaction endothermic or exothermic? Well, if you look at this, the energy of the reactants is more than the energy of the products. Some of that energy has escaped into the wild to heat up the surrounding molecules. So it could be the thermometer you're using to measure the temperature. Okay, so this is an exothermic reaction because the products have a lower energy than the reactants. Okay, it's exothermic because the products have lower energy than the reactants. D, the reaction between zinc and dilute sulfuric acid can be catalyzed by the addition of aqueous copper 2 sulfate. On the diagram, add the energy profile for the catalyzed reaction. Now, the key thing about catalyzed reactions is the activation energy is lower. It takes less energy to start the reaction. So the energy profile goes up, and basically the hump is lower. That's all that they're acting for. That's all that they're asking for. This is the catalyzed reaction. All right, that's all that they're looking for. E, a student electrolyzes aqueous copper 2 sulfate using the apparatus shown. Okay, so it's electrolysis. Before you even read the rest of the question, I always start off by making sure I panic. So we have the positive anode, negative is the cathode. All right, it doesn't even matter what the questions are. That generally comes up somewhere in an electrolysis question. So oxygen gas forms at the positive electrode, the anode. Write an ionic half equation for the reaction at the negative electrode, the cathode, and include state symbols. Okay, so you didn't need to panic in this one, but it's always worth remembering. That's the only time you should panic in a science exam. Okay, so the ionic half equation. So it says the oxygen gas forms at the positive electrode. We have copper 2 sulfate, CuSO4. At the negative electrode, we're getting our copper, our aqueous copper, okay? And turning into a solid copper. Okay, so we have Cu2+, and that's aqueous. So copper ions dissolved in water that are blue, because when they're dissolved in water, they're blue, plus 2 electrons that balance out these 2 positives, produce Cu solid. Okay, that's the half equation they're talking about. So if we write that in here, Cu2+, aqueous plus 2 electrons produces CuS. Good. And describe what the student observes at the negative electrode. Well, at the negative electrode, you can say a pink or brown, a pinkish brown solid forms. So it coats the electrode. Give 2, and so that's at the negative electrode they're asking for. So that's the one that they want there. But here they want to give 2 other observations which the student makes during the electrolysis. Okay, first of all, the student will see bubbles of oxygen gas. Okay, the bubbles of oxygen gas will form at the anode. Okay, and the other thing that they see is that the solution becomes paler. The blue color disappears. So that's as the copper ions are used up. All right. So what difference would the student observe at the positive electrode if the aqueous copper 2 sulfate were replaced by concentrated aqueous copper 2 chloride? Okay, so the difference here, copper 2 sulfate, SO4 minus, compared to copper chloride, Cl minus. The chlorine, the Cl minus, produces chlorine gas, okay, and rather than the oxygen gas. And so the chlorine gas is a green color. So a green gas would be seen, which is the chlorine gas. All right, so let's move on to question 6. Question 6. The table shows the structures of 4 hydrocarbons, P, Q, R, and S. Why are compounds P, Q, R, and S known as hydrocarbons? Okay, it's because they only contain carbon and hydrogen. Hydrocarbons, carbon and hydrogen. So they only contain carbon and hydrogen. That's it. B. Compound P is saturated. What is meant by the term saturated? Well, as you can see in compound P, there is one single bond, C. Compound Q has a double bond, R has a double bond, and S has a double bond. So saturated means that there are only single bonds. So it only has single carbon-to-carbon bonds. Okay. C. Compound P undergoes a substitution reaction with chlorine. Okay, what is meant by the term substitution reaction? Okay, substitution reaction is when one atom or a group is replaced by or substituted for another atom or group. All right? Okay, so one atom or group is replaced by another atom or group, and by replaced it means substituted. So it's substituted. 2. State a condition required for this reaction to occur. Okay, so this reaction generally occurs in UV light or sunlight. So substitution reactions often occur in sunlight. Okay, so write a chemical equation for this reaction. Okay, so chemical P, that is C2H6 plus chlorine, as it said. Cl2 is chlorine gas. Produces C2H5Cl plus HCl. And if you notice, one of the chlorines has swapped with one of the hydrogens. And that's it, it's been substituted. D. Compound R undergoes an addition reaction with bromine. 1. Why is this reaction an addition reaction? Okay, so if you look at this, we have C, double bond C, and we have H. So this is compound 2, CH2CH2. Okay, so it's called an addition because Br, that's the molecule that you're adding, just one goes here and one goes here. Okay, so it's adding over the double bond. Okay, it's breaking the double bond and adding it. The reason why it's called adding is because you start with more than one molecule and you add them together to make one molecule. You're combining them into one. So there's only one compound formed. Okay, so a compound containing bromine is found in this reaction. Draw the structure of this compound and show all of the atoms and all of the bonds. Okay, so compound R, you're starting with, you have C, double bond C, single bond C, so 3 H's here, then 1 H can be either above or below, and then H here and H here. Okay, that's what you're starting with. This, you don't need to show this in your answer. This is just your starting structure. Okay, and it's going to break this double bond, and on one carbon it's going to add a Br, and on the other carbon it's going to add a Br. Okay, and it doesn't matter if you put this Br at the top or the bottom, it doesn't matter. Okay, so what it wants to see in the answer, you have 3 carbons in a row. All right, so we started off with H at this side, H on one, Br, and it doesn't matter if you have Br above or Br below, it doesn't matter at all. And then we have H, Br, and it doesn't matter, you can have Br over here, it doesn't matter because this twists, this spins, this carbon. Okay, so this, you don't need to show this in your answer. This is what they want to see. Okay, good. E. Draw the structure of an unbranched isomer of compound S. Show all of the atoms and all of the bonds. Name this unbranched isomer of compound S. Okay, just to refresh your memory, Compound S is CH2 double bond CH CH2 CH3. All right, so an isomer is all the same atoms, but in a slightly different order. So, but the same, and the same bonds, but in a different order. Okay, and it says unbranched, which means you can't put one of these carbons over here, because if you were to put that C down here rather than over there, that would be a branch. Okay, so an unbranched isomer. So if we look at this molecule, the easiest thing to do to make an isomer, or the only thing you can really do to make an unbranched isomer, is to move this double bond over here. If you move this double bond over here, it's exactly the same molecule as it started with, just turned a bit. So we don't want to put it over there. All right, so how do we do this? So we need to show all the bonds. So this is not showing all the bonds. Okay, so we have a single bond, then we put a double bond, and then we put a single bond. And then we just add hydrogens so that every carbon has 4 lines coming from it. So we have 1, 2, 3, 4. So these are then hydrogens. That is 1, 2, 3, 4. Doesn't matter if this H is on top or on the bottom. Same thing. 1, 2, 3, 4. That's okay. This hydrogen can be on the bottom. And then 1, 2, 3, 4. These 3 have to be hydrogens. And that's all it's asking for. Okay, so now we need to name this molecule that we've just created. And you have to first of all start with how many carbons are there. Is it a meth, eth, prop, or bute? Okay, and how do you remember which order they go in? I like to say monkeys eat peeled bananas. Methane, meth, eth, prop, bute. Monkeys eat peeled bananas. So if there's 4 carbons, there's bananas, it's bute. And it's bute. Next thing we do is we find out which carbon the double bond is on. Here it was on carbon 1, or over here it'd still be on carbon 1. But this one's on 2, so it's bute 2, and it's a double bond. So bute 2-ene. Okay, good. F. Compound Q undergoes polymerization. Name the polymer formed. Okay, let's look at this. Starts off this is compound Q. Monkeys eat, there's 2 carbons, so this is ethene. Okay, ethene. We don't have to say ethene, S1-ene, because there's only one spot it can possibly be in. So ethene, and if it's a polymer, it is polyethene. And that's it, polyethene. Okay, to complete the chemical equation to show the polymerization of compound Q. All right, so we start with, it's polymerized. We have CC. It just keeps going. Those CCs will keep going. And above here, we'll have an H, 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 H. But the double bond has been broken, and now it's attached to another CC with HH. Another C, and one on each side, and many, 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 many. So what we do is we just kind of say, yeah, it keeps going on for n number of ethene monomers. Okay, so the n there goes here to say it just keeps going on and 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 on. All right. G. Amino acids undergo polymerization to form proteins. Part of a protein molecule with the linkages missing is shown. Draw the linkages on the diagram. Show all of the atoms and all of the bonds. Okay, so if you remember, with proteins, start off with one side. We have C, double bond O, OH. That's the carboxylic acid side. We have our middle bit that can change, and we have NH, H. So this is one amino acid. This is the amine side, the N side, and the COOH is the acid side. If we add another one of these, it could have a different middle bit. COOH to NH2. Then what happens is these two come together and give us water, and those join together. So what we have here, we have an N on this side, so we have to have a C on this side, and then an N, and if there's an N on this side, there has to be a C on this side. And then there's an N, and to double check, there's also a C on this side. And attaching to the ends, we have H's, and attaching to the C's, we have double bond O's. Okay, and these are known as amide or peptide links. Amide link, amide bond, or peptide link or peptide bond. Okay, same thing. Good. And finally, H. The structure shows an ester. Write the word equation for a reaction which could be used to make this ester. Okay, now the key thing with esters is this bit is created using a carboxylic acid, and that has to be COOH, and this bit is created using an alcohol. So carboxylic acid and an alcohol produces an ester. Okay, so we have butanoic acid. So again, on this side, 1, 2, 3, 4, monkeys eat peeled bananas, says B. That's butanoic acid, okay, plus 2 carbons on this side, monkeys eat, it's E, ethanol, produces ethyl butanoate, plus, so this would be C, that would have an OH there, and that would have an H. Those OH and H join together to produce water. All right, so butanoic acid plus ethanol produces ethyl butanoate plus water. And that is the end of this paper. I hope you found that helpful. If you enjoyed that, or you did find it useful, please like and subscribe to let us know. Also, if you have any comments or anything you'd like to ask us, or any other question you'd like us to go over, write them in the comments below, and have a great day.